So here is two graphs of full-time post-secondary enrollment in Canada. The red graph represents people who are enrolled in colleges, and the blue graph represents the people that are enrolled in universities. So if we scroll down here, we can see in 2004, just over 60 million were in colleges, and just over 10 million were in universities. And if you wanted to do graph plus graph, the question would ask, how many total people are in post-secondary? So if I add 6 million plus 10 million, I get just over 16 million. And in 2005, it's a little bit more. In 2006, it's almost, looks like it would almost be 17 million. And then in 2007, looks like it would be. And in 2008, it will be over. And when adding graphs, we just add the y values. So it's not, I hope, if you were hoping for something really complicated and exciting, sorry, it's really easy and boring. When you're adding graphs together, all you're going to do is add the y values. Because this graph we could call f of x, and this graph is g of x. And so if you did f of x plus g of x, does it make sense that f of x is just the y values of the red one, and g of x is just the y values of the blue one? So when you're adding them together, you're just adding the y values. And this would be an example of a situation where you could have two different graphs of two different y values and want to add them together to get the total. Now we get one with subtracting. They give us an equation here. They say that the stopping distance for a car is a function of the speed of the car when the brakes are applied. Now, if you imagine you're going in a car and something jumps out in front of you and you feel the need to stop, right? You react. It takes you a little bit of time to react, to lift up your foot and slam on the brakes. In that tiny millisecond, hopefully the quick reaction, your car still moves forward. That's called the reaction time distance, which is here in blue. Then you slam on your brakes and you slide, because nobody has a car that when you touch the brakes stops immediately. That would be kind of scary. If you had like some sort of anchors in your car that you touch the brakes and they just drive them right into the ground and your whole car stops immediately, then you would probably die. So when you brake, you slide a certain amount, and that is called the braking distance, which we're going to do in green. And if you take the reaction distance, which is the blue one, and add the braking distance, well, this is like adding that we just did. You would add those y values, and you would get your stopping distance, which is shown in red. So we have, I'm going to use S for stopping distance is equal to R for reaction plus speed for braking. And of course, with an equation, you can rearrange things. What graph don't we have? We don't have the green one. Does it make sense that your green graph will equal your red graph minus, or sorry, your complicated with all the colors. Does that make sense then? If you rearrange that equation, your green graph would be the stopping distance, the total amount of time it took to stop. If you subtracted your reaction distance, then what you would be left with is your braking distance. So let's look at certain situations here. Let's look at driving fast. If you're going 100 kilometers an hour, you see something jump out in front of you. You react. But in that, because you're going so fast, even though you react super quick, you still travel 20 meters before your foot even touches the brakes. So if whatever jumped out in front of you is within that 20 meters, it does not matter. You don't have any chance of stopping before that. Then you slam on your brakes, and slamming on your brakes, you will travel another total of 90. Does it make sense then that you would have, if you went 20 already, you would have slid 70 while doing your brakes, and that the blue and the green together have to add up to the red. So again, subtracting, same as the adding, and we're going to find this with all operations with our graphs. We're just going to work with our y values. So the red minus the blue would take you 70 meters before you stopped, and it looks like 90 meters in total. Which is kind of scary to think that if anything jumps out of you within 90 meters and you're going 100 kilometers, even if you react right away, you're probably going to hit that. I like this one. You are in a parked car, not driving at all. Something jumps in front of your parked car, and out of instinct, you react. And slam on your brakes. And during the time that you react, you do not move forward at all because you're in a parked car. And you slam on your brakes, and you're already stopped. So all three of those are at 0, which should make sense. But we can go through the rest of these and sort of say, okay, well here I've got about 58 minus 15 would be about 43. And here I have 35 minus 12 would be about 23. 20 minus 8 would be 12. 9 minus 4 would be 5. And we can draw our braking distance graph in here as well. Yes?
You just subtracted the y values of the red and you hit the green?
That's right. So this is an example of subtracting graphs. When you're adding graphs, you just add the y values. Now we're just subtracting the y values of the graph. The next one, they didn't give us a situation, a story. They just gave us two graphs, f of x and g of x, and said, can you draw the green graph that multiplies them together? So again, the idea stays the same, but there's going to be some strategies that make your life easier or harder when doing this. For example, you might not choose the points 2.87 and 3.94 for multiplying, because mental math, that's not easy. What are easy values to multiply by? Sorry? 1. Okay? So when a function is 1, let's look on the blue graph. The blue graph is 1 right here and here, and the red graph is 1 right there. If one of them is 1, when you multiply by that, it doesn't change. So my green graph will be here when the red one is 1. And here when the blue one is 1. But it does not even exist at the other blue point because the red graph doesn't exist. So first of all, both graphs need to exist. But when one of them is 1, so let's just look at this example here. When the x value is 1, on the red one, the y value is 1. On the blue one, the y value was -1. And if you took the two y values and multiplied them together, what's 1 times -1? Here we can write it out. 1 times a -1 is going to equal, on my green graph, -1. So that's why my green graph is exactly where the blue graph was. Now, for the next point, looks like when x is, I don't even know what the x value is, and it doesn't matter. When x is about 2.3, that's when my blue graph was equal to 1. And my red graph, I'm going to have to estimate it, looks like it's about 1.4. And if I multiply 1 times 1.4, I'm going to get 1.4. So my green graph is on my red graph in that situation. So when a function is 1, it's going to just be equal to where the other graph is. That's pretty easy to do mental math. What other mental math ones are easy to multiply by? 2's not bad. There's one easier than 2. 0. Like, I have such a good zeros times table. I've like worked up into the thousands already. Like, test me 0 times any number in the thousands. Try. 0. See, it's been practicing. So definitely super easy when a function is 0. So now I'm going to go on my red graph, I'm only 0 once. On my blue graph, I'm 0 twice. So my green graph is definitely going to have those 2 points. Because you multiply by 0, you're going to get 0. Now you can do other ones. Those are the nicest. When something is 1 and when something is 0. We could do other points. Like I could, let's look at, this one is 3, right? And the red graph looks like it's 1.8. What's 3 times 1.8? 5.4. We could do that for 5.4. And by multiplying a bunch of y values, we get an idea of what our graph is. But unlike the adding and subtracting, this is a little bit more complicated. And we're going to use, right? Guess we can. I like using this idea of nice points. Even if they're not so nice, you can still just, all we're doing is multiplying the y values. But when doing this, to get an idea of what the graph is, we need to make sure that we see which values we can multiply the easiest. And definitely when something is 1 or 0, that makes it the easiest. Now, it asks for the domains of each of these graphs. So I'm going to start with the blue one is a parabola. Its domain would have been everything. The red one is a square root graph. Its domain was when x was bigger than or equal to 0. And we notice on our green graph, its domain is also when x is bigger than or equal to 0. The idea is, if you're adding, subtracting, multiplying, or dividing two graphs, your new graph can only exist if both the original ones exist. So since the red graph doesn't exist when it's negative, the green graph doesn't exist when it's negative. right? I can give you examples of this with real numbers. If I multiply one thing that exists and one thing that doesn't, you tell me the answer. Okay? What's 5 times?
5 times 3.
No, I didn't say that. I said, what's 5 times?
1. 5 times 1.
Right, if I don't give you the other number, it's impossible to do, right? That's why this graph doesn't exist on this side. Because I have the blue graph, but I don't have the red graph. Right? And you were like, waiting for me to say something else. Right? Times 2.
What times?
Yeah, what times 2? It doesn't, if you don't give that other number, you can't actually have it. That shows up in the graphs as well. Okay. Now the most complicated one is dividing. The rule stays the same. But let's think of certain things that are going to be, strategies. Let's look at some strategies. What are things that are easy to divide or easy to divide by? Divide by 1, okay? In this case, I'm going to color code here. The blue one is on the bottom. F of x is the red graph, it's on the top. So if we're dividing by 1, that would be where the blue graph is 1. Why is that easy to do? Okay, I'm going to go on my graph. Here my blue graph is 1, and here my blue graph is 1. Well, because your times table is pretty good with 1s as well, probably, dividing by 1 just keeps something the same. So, does it make sense that if I'm dividing by 1 here, my red graph might just go straight up, it would be exactly the same as my red graph. Because if the red graph looks like what? 2.8, and the blue graph is 1, 2.8 divided by 1 still says 2.8. Those points are going to stay the same. That's a good strategy. What other things are easy to divide? Can you divide by 0? We're going to write this down. What happens when you divide by 0? We just did. Dividing by 0 is not 0. Dividing by 0 is not allowed. That's a non-permissible value. What happened in our rational unit when we had non-permissible values? It was either an asymptote or a whole. Okay? Almost always in this unit, it ends up being an asymptote. The only way it would be a whole is if both of them, if you had, I'll just put it in brackets here, maybe a whole if you have 0 divided by 0. But anything divided by 0, anything other than 0 will become a vertical asymptote. So on our graph, since we're dividing by the blue one is 0 here and here. So I'm going to take out my red pen. And I'm going to draw vertical asymptotes at -3 and at 3. With the adding and subtracting, you can be pretty confident after a couple of points that you think you know what the graph is going to look like. Multiplying, you probably have to do 3 or 4 points, and you start to feel you know what it looks like. With the dividing one, I hope you're feeling right now that you have no idea what it looks like. We've got 2 points and 2 asymptotes. So we're going to need more strategies. Okay? So dividing by 1, dividing by 0. Of course, you can always do nice points, but I'm going to also say another good strategy when the numerator is 0. What do you get if you have 0 divided by anything? Right? You have lots of friends and you really like to share, but you have $0. So you decide to share all your money with all your friends. How much do they each get? Nothing. 0 divided by anything is always 0. So now we're going to look, where is the red graph? 0. Because this I would have 9 divided by 0. This is actually nice enough point. No, sorry, I'd have 0 divided by 9. The red graph divided by the blue one. 0 divided by 9 is 0. All right, do we feel comfortable with what's happening here? Probably not yet. Are there any other points that look like you could do that are nice? I think this isn't bad. Here I have 8. Here I have 1. And if I'm doing the red divided by the blue, I would get 1/8. Same thing on this side. So we could do some other points. Let's say, oh, look at this. Here my blue graph is 5. My red graph is 2. What would you get if you did 5 divided by 2? Oh, sorry. The red one's the one on top. Sorry, 2 divided by 5, you would get 2/5. 2/5. 2/5. So we can do some nice points. You should write that down because that's also a good strategy. But there is a place on the graph that has not nice points, but the answer is nice. Where do I have on the red and the blue graph not nice points, but I guarantee you that you can do the math with, even if I gave you 80 decimal places at these not nice places, you could still do the math. Where would that be on the graph? Where they cross, where they intersect, okay? If I gave you 80 decimal places, they look like they intersect here at 2.5, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Divided by 2.5, 1, 2, 3, 4, 5, 6, 7, 8. What's the answer that you're going to get? You're going to get 1. So, where they intersect, you have the same number divided by the same number. Right here is where they intersect. I'm going to put a little black dot where they intersect. And on my graph, that for sure is going to be at 1. I hope in the middle you're feeling pretty good. You've got asymptotes. Your points really seem to match up that they're going to look like this. But you see, just like in rational graphing unit with the dividing, you've only done one section. We've only done section 2 here. Can you see that the vertical asymptotes made a section 1 and a section 3 that we need to graph as well? So again, we can take some nice points in these sections. It looks like here, I would probably choose this point. Here my y value is -1, and my red one looks like it's 3 point something. 3 point something times a -1 will be -3 point something. We're not multiplying, we're dividing. Sorry, let's start again. The red one is 3 point something, divide by a -1 is going to be -3 point something. So I get another dot down there. Another strategy. Is the dividing one, do you think, the hardest? Because we still have 2 sections we haven't done. This is a good unit because it does review a lot of units that we've done already. Use the functions and the rational graphs unit to figure out what the graph should look like. On this side, in section 3, can you see that the red one is a line, a straight line? And the blue one is a parabola. So if you had in your rational functions unit a line divided by a parabola, what do you remember? Right? That would mean the degree is bigger on the bottom. Would you have an oblique asymptote or horizontal asymptote? Horizontal asymptote. And if it's bigger on the bottom, this means that you would have a horizontal asymptote at y equals 0. We can add that into our graph. And once, if I had this, and I had a nice point, which I do in this section, I could graph the rest of that. And same thing, I'll find a nice point in this section, and I could graph the rest of that. Yes?
What's the nice point in the third section?
The third section there that I would use, and I'll write it out. The nice point that I have is on my blue graph. On the blue graph, I had -1. So I'm using this point right here. I'll make it really big. My blue graph is -1. My red graph isn't super nice, but it looks like it's at 3.1. And if you did 3.1 divided by a -1, you would get -3.1. And that's the green point down there. So that's the nice point. And you could similarly find a nice point in the other section. So this is 4.1. And in the assess the understanding, good questions for practice are question number 1. Question number 1 is interesting because in part D it does have a hole. So you might want to, on number 1 in D, just put in brackets there that you should get a hole. Number 1, 2, and 3.